All right, avid Wildcats, we are on page 194, Chapter 5, Lesson 2, Heating Earth. So you put your name, subject or class period, the date, I believe Tuesday is going to be January 19th, 2021, our topic or objective, Science FNT, Chapter 5, Lesson 2, Heating Earth in blue. All right, the title is blue. Use your blue pen, pencil, crayon, marker, whatever. Make it blue. If you don't have one, go down to the 99-cent store, buy a little package of crayons or colored pencils, borrow some from a little brother, sister, cousin, something. Get it in that color. Okay, the main idea or essential question. For many reasons, energy from the sun does not heat Earth evenly. So, energy from sun not heat Earth evenly. Doesn't have to be a complete sentence, right? This is our notes. Our first vocabulary word or term, greenhouse effect. Greenhouse effect. So we write that there. It's on page 198. There's 198, and here it is. Go backwards to the beginning of the sentence. This mechanism for warming the surface and lower atmosphere of a planet is known as the greenhouse effect. Okay, so we are warming surface and it's the low atmosphere. So the greenhouse effect warms the surface and lower atmosphere. But they were saying something about a mechanism. I don't know what that mechanism is. Let's go figure it out. Keep going backwards. Keep going backwards. All the way to the beginning of this little paragraph here. On a much larger scale, certain gases in Earth's atmosphere act somewhat like the glass panels of a greenhouse. Like the glass, these gases allow radiation from the sun to pass through and warm the Earth's surface. Earth's warm surface radiates energy back into the atmosphere as infrared radiation. The gases absorb most of the infrared radiation, letting only a little of it pass through to space. The absorbed radiation is re-emitted in all directions, warming the surface and lower atmosphere. Okay, so here's kind of a picture of what they mean. The sun's radiation comes in, hits the surface of the Earth, and warms it up. That infrared radiation, remember that heat or that warmth we talked about in the previous lesson? Warms up the air, warms up the surface, warms up the clouds, and all that warmth stays here to keep the Earth a little bit warm. It doesn't just automatically go back out into space. A little bit of it does, but the greenhouse gases keep some of it in. Okay, so radiation passes through atmosphere. Okay, remember I said that right here. Radiation pass through atmosphere. Okay, then warm surface, arrow, IR, arrow, warm atmo, period. So the warm surface of the Earth causes infrared radiation or heat, which warms the atmosphere. Okay, so where did they say that? Earth's warm surface, there's warm surface. It goes back as infrared radiation, there's that IR. And then that helps warm the surface and lower atmosphere. So warm surface, arrow, IR, arrow, warm atmo. The warm surface emits infrared radiation, which then makes the atmosphere warm. All right, let's go ahead and start our first section. Uneven heating. Red pen, red pencil, red crayon, borrow one from a cousin, go to the 99-cent store, find something and make it that red color. Uneven heating. Uneven heating. From moment to moment, the sun emits about the same amount of energy. When sunlight strikes Earth, some of the energy is absorbed by land, water, and the atmosphere. The absorbed energy is changed to thermal energy, heating Earth. Okay? Sun emits same amount. Some absorbed, land, zoop, water, zoop, atmosphere. Thermal, arrow, heat. So the sun emits the same amount of energy most of the time, Some of it gets absorbed by the land or the water or the atmosphere. And all that thermal energy helps heat the Earth and keep things warm. So why does Earth have such a variety of weather? How can the same day be warm and pleasant in California, icy cold in the far north, and steaming hot near the equator? The reason is that Earth is not heated evenly. Earth heated unevenly. At the equator, sunlight strikes the surface at a 90-degree angle. Okay, here's an example of that. At the equator, it hits at a 90-degree angle, straight on. As you move north toward higher latitudes, Earth's surface curves away from the equator, so sunlight strikes at an increasingly smaller angle. As a result, the same amount of solar energy is spread out over a larger area. Okay, so we said 90-degree angle straight on here. Here it's tilted away a little bit, so it gets spread out over a slightly larger area. Way up here in the Arctic, it's really tilted away from the equator, so it's getting spread out over a much larger area. Look at how this little circle is actually quite a bit smaller than that big giant oval of land right there. So the same amount of energy is getting spread over a much larger area. Okay? That larger area actually makes it colder. All right. So we're going to draw a little picture here. So I drew a picture of the Earth by making just a circle. That's the circle of the Earth. A little dotted line for the equator. It's kind of tilted. A dotted line for the equator. Two little nubs here for the axis that the Earth spins or rotates on. And then instead of 3 beams, I just drew 2 beams. A little circle and a beam. And I bubbled in this circle at the equator. Then I made a circle and a beam. And I made a big oval up here at the top. Notice how it has a lot more surface area than this. And I drew an arrow over here and I said, higher latitude, arrow curves away. Remember they said that the Earth's surface curves away at higher latitudes? Energy spread out. So they said that energy spread out. Okay. To state this another way, the amount of solar energy per square meter of Earth's surface is greatest at the equator. It decreases as you move away from the equator. A square meter of land near the North Pole or South Pole receives little solar energy. Okay, so if you take a little patch of land at the equator, it has a lot of energy because it's hitting it straight on. If you take that exact same size of a little patch of land, a little square meter up here, it's receiving less energy because all that energy is getting spread out at a different angle. So what I wrote was energy per square meter at, that's the letter A with the circle around it, equator, greater than energy per square meter at pole. The energy per square meter at the equator is greater than the energy per square meter at the poles. In other words, it is hotter at the equators and colder at the poles. Okay, here we go. Another angle effect occurs because of Earth's rotation about its axis. The air is cooler in the morning and evening when the sun is low in the sky. The hottest time is often around noon, when the sun is most directly overhead. Okay, so same angle effect, rotation. Morning cool, arrow, afternoon hot, exclamation point. So what we're saying is that same angle effect is happening because of the Earth's rotation. In the morning it's cool, but in the afternoon it gets really hot. Same thing's happening here, right? If you're at the equator, that's like noon. That's super hot. But if you're at the poles, that's like either the morning or the nighttime. It's getting cooler. The same is happening as it's rotating east to west. Okay, so the tilting is the same, and you're getting that same angle effect with the rotating also. Okay, in any given place, the sun changes position in the sky because Earth curves toward or away from the sun as it rotates. When the sun is high in the sky, its rays strike Earth most directly. During the morning and evening, however, the rays strike at a smaller angle. This spreads solar energy over a greater area. So, they're talking about that same angle effect happening because of the rotation. They're talking about the morning cool and the afternoon hot. Okay, when sunlight travels through the atmosphere at an angle, the light has to take a longer path through the atmosphere. Okay, so if you're looking at the equator, there's a little bit of atmosphere right here above it. But if you're up here, oh, it's got to travel through the atmosphere at an angle. It's a longer path through the atmosphere. A longer path means that the light has a greater chance to be absorbed, reflected, or scattered. Less light reaches Earth's surface. Okay, so angle, arrow, longer path. Atmo, period, absorb, / reflect, / scatter. So just like how they talked about at an angle, it takes a longer path. At an angle, the light takes a longer path. So the atmosphere can absorb, reflect, or scatter some of that energy. Absorb, reflect, or scatter. So really you've got at least three things going on. You've got whether the light is up here at the pole or the equator, so the angle of the land that it's hitting. Then you also have the Earth rotating, whether it's morning, noon, or night. And then you also have how thick the atmosphere is, or what path the light has to take through the atmosphere, a short path or a longer path. And all of those stack up to make the equator hot and the poles cold. Okay, let's keep going. A third reason why Earth is unevenly heated is because its axis is tilted. As Earth moves through its orbit, it is tilted either toward or away from the Sun. As you learned in Chapter 1, this causes the seasons. For example, when it is summer in North America, the northern hemisphere is tilted toward the Sun. The days are longer and the Sun is higher in the sky, resulting in more sunlight per square meter. Okay, so tilted axis. Close equals summer, long days. Far equals winter, short days. Okay, so in this picture, it kind of looks like it's getting to be winter since it's tilting away. So we have your latitude changes, how much energy you're receiving per square meter. The Earth rotating changes how much energy you receive in the morning versus the noon versus night. The tilt changes how much energy is passing through the atmosphere quickly, or it takes a longer path, and so more of it's getting absorbed or scattered. And the tilt affects the seasons, right? If it's winter and you're tilted away, you're getting less. If it's summer and you're tilted towards, you would be getting more. Lots of stuff going on. All of that, all working all at the same time. Okay, why do different places on Earth receive different amounts of solar energy? Different places on Earth receive different amounts of solar energy for many reasons. For example, the land, water, and atmosphere absorb some of the sun's energy. The Earth is heated unevenly because at higher latitude, the land curves away, so the energy gets spread out. In other words, the energy per square meter at the equator is much more than the energy per square meter at the pole. So the equator's hotter and the pole's colder. You get the same angle effect with the rotation, meaning that in the morning, you're kind of angled far away, so it's cool. In the afternoon, the light is hitting you straight on, so it's hot. And then as it goes towards night, it angles away again, and it gets cooler again. Also, the angle of the Earth causes you to have a longer path at the poles, so the atmosphere can absorb, reflect, or scatter more energy. And then the tilted axis also causes seasons. When you're tilted closer to the sun, you get summer and longer days. When you're tilted farther away, you get winter because of shorter days. Okay, let's keep going because we have a lot of pages. As you notice, it's not just a 3 set, it's a 4 set, and we have a short week, so we're going to have to keep going. Earth's energy balance in red. Again, pen, pencil, crayon, borrowed from a cousin, got at the 99-cent store, something. Find something red to make it that red color so it stands out to you and it's easy to see. As you have read, get it, red? Earth receives only a tiny fraction of the total energy that the sun gives off. However, this small amount is enough to power Earth's water cycle, create weather, and provide the energy that plants and other living things need to grow. Okay? Tiny fraction actually received. Water cycle, weather, life. We indented, right? So a tiny fraction of the sun's energy is actually getting received. Tiny fraction actually received. And that causes things like the water cycle, weather, and allows life on Earth. When sunlight strikes your skin, you'll notice that your skin feels warm. This happens because the sunlight absorbed by your skin is changed into thermal energy. Your skin is not the only thing that absorbs sunlight and becomes warm. This happens to the Earth's surface, too. As shown in the diagram below, boom. Only some of the sun's radiation reaches Earth's surface. This fraction is eventually re-radiated as infrared radiation. On average, the amount of energy Earth receives from the sun balances the amount it loses into space. That is why average global temperatures don't vary much. So in other words, a lot of energy is coming in, but on average, the amount of energy getting absorbed by the land and the clouds and the ocean balances out how much is getting lost over time by infrared heat going out into space. Okay, so energy absorbed equals energy lost. Earth's temp, TEMP for temperature, wiggle line, steady. So the amount of energy absorbed as it comes in from the sun is equal to the amount of energy lost out into space. That makes the Earth's temperature pretty steady over hundreds, thousands, even millions of years. Okay, the diagram presents an average energy budget for the entire Earth. So what they're saying is this diagram shows energy coming in and energy going out and how things kind of balance out over time. For any given place, actual numbers may vary a lot over time. On cloudy days, for example, the clouds reflect incoming solar radiation back into space. That is why cloudy days are cooler than clear days. Clouds at night have the opposite effect. At night, Earth's warm surface emits infrared radiation into the atmosphere. Okay, remember, so the land has absorbed a bunch of energy. At night, that infrared energy is getting emitted back out as warmth. If you have clouds, the clouds absorb that radiation and re-radiate some of it back toward the surface. That's why cloudy nights tend to be warmer than clear nights. On clear nights, radiation from the surface escapes into space. So if you had cloud cover, that reflected or re-radiated energy from the surface will hit the cloud and it'll be kept there. If it's a clear night, that re-radiated energy just goes back out into space and gets lost. As a general rule, light-colored surfaces such as clouds, snow, and ice tend to reflect more light than dark-colored surfaces. Okay, before we talk too much about this, let's go back to this thing, all this stuff about the clouds. Okay, in the middle, draw a little cloud and put clouds, an arrow to IR for infrared, and an arrow towards warm night. So if the clouds absorb some of that infrared energy, they can re-radiate it and create a warmer night. Okay? But in the day, the clouds can reflect some of that energy back out into space and create a cooler day. So let's put that reflect back to space. Reflect back to space. There we go. And over here we're going to say R-E dash radiate. R-A-D-I-A-T-E. So it re-radiates that infrared, creating a warmer night. All right, now let's talk about the surfaces. Light-colored surfaces, such as clouds, snow, and ice, tend to reflect more light than dark-colored surfaces, such as forests or the ocean surface. These differences also help explain why Earth's surface is heated unevenly. So, light, reflect, clouds, snow, ice, dark, absorb, forest, ocean. So clouds, snow, and ice tend to reflect more light back out into space, while forests and oceans tend to absorb more of that light energy. So forests and oceans can absorb more energy and kind of keep that energy into the Earth. All right. Only about half of the incoming solar energy reaches Earth's surface. What happens to the rest? Interesting. Okay, so 51% absorbed by surface, 19% absorbed by atmosphere and clouds. If I move that 1 over here to the 19, I have 20. 50 and 20 would be 70. 74% reflected by surface, reflected by atmosphere and clouds. So 74 plus 6 would be 80, and then 80 plus 20 would be 100. So this is kind of that energy balance. If you take all the energy from the sun that gets to Earth, about half of it is absorbed by the surface, about 20% by the atmosphere and clouds, a small amount gets reflected by the surface, and about 1/4 or 1/4 gets reflected by the atmosphere and clouds. All right, that will be good for day 1. It was a long video, but it's going to help us keep on track so that we'll have plenty of time to write our paragraph towards the end of Thursday and Friday. Good job persevering with the growth mindset. Roar, Wildcats!